Hi, I'm Olivia, everyone's favorite math teacher, and in this video we're going to be talking about function families and their properties. So when we say function families, what we're talking about are mathematical models, and we group them in families based on their general properties. So I've put them into four main groups based on how we tend to look at them in calculus. Up into this area where I've got its power and root, this is all the things that are like your linear functions, all of your polynomials, your basic power functions, and of course anything that would be the inverse to your power functions, square root, cube root, all of that kind of thing. Over here, your rational functions, that's polynomial divided by another polynomial. Of course, can't have a denominator of 0. We'll get into that later. Down here, we have your exponential functions and your logarithmic functions. That's all of your interest formulas, any exponential growth things. And then, of course, we have your standard logs and your natural logs. This is where you're going to typically be working with Euler's number. And then over here are your trigonometric functions. You'll notice I've only included the three most basic, like I don't have your cosecant, secant, and cotangent. Those are included as well. I also have only included what we call the parent function versions. These are the most vanilla, and this is what we're going to be looking at next when we look at the function along with its graph to look at the basic features. The more advanced features we're going to be looking at in the next video when we look at transformations and operations with functions. First up, we have our linear function. This is a first-degree polynomial characterized by a straight line graph, notable for the fact that it has a constant rate of change that we call the slope. Next, we have a second-degree polynomial function. This is characterized by its U-shaped graph that we call a parabola. Very notable feature is the vertex, which is the point located at the very bottom middle of the graph. This is where the line of symmetry is for this particular kind of graph. Next, we have the third-degree polynomial function. This is the cubic function. And the thing that I hope you've noticed here is that odd-degree power functions have end behavior where one side will point down, the other side will point up. Even power functions will have end behavior where both sides will point up or both sides will point down. That'll come up later. Okay? Next, we're going to look at the root functions. The square root function, you'll notice, starts at the origin and then heads off going up, but unlike the cubic or the square function, this one gets slower while still constantly increasing. Then we have the cube root function. On the positive side, it kind of looks like the square root function, but this one has a tail going off on the negative side. Or another way to think about it is, it looks like a sideways cube function. Okay. Next up, we have the rational functions. So all of these functions, you'll notice, are characterized by the fact that they have what we call asymptotic behavior. This means they have asymptotes. These are the parts on the graphs you see where they're heading off into some weird line. Or you might not see it, but in that graph, where it doesn't look like there's anything weird going on, there's actually a hole that you can only find if you try to go to the specific point where the graph has actually had a section of it that we can factor out of the original function. More on that later. Okay. Next up, we have the exponential graph, and this kind of looks like it starts out slow and then shoots off like a rocket. This is the characteristic of exponential growth. Now, the key points on this graph that you need to pay attention to are the fact that it goes through the point 0, 1, because of course, if we take any value and put it to the 0 exponent, it's 1. And then also notice that it has horizontal asymptotic behavior at x or y equals 0, meaning that as you try to go towards 0, you can't because, well, you can't get a value of 0 out of the graph. And then next we have the log. This is the inverse of the exponential, and it has the exact opposite characteristics. Instead of growing very quickly, it starts growing fast and then slows down its growth, still growing though. That's very important to notice. And instead of going through the point 0, 1, it goes through the point 1, 0. Inverses. And its asymptotic behavior, instead of being at y equals 1 or 0, is at x equals 0. Okay? And we're going to finish off with our trigonometric functions. We're going to start with sine. This is the classic wave graph that starts at the origin at 0. We have cosine, same kind of wave graph, only this one starts at 1. And here's the cool thing. You kind of put them together and it looks a little bit like a double helix, right? And then we're going to finish off with tangent. Now, when you look at tangent, this one's really weird, but the interesting thing here is it has asymptotic behavior at every odd pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2 is an asymptote. And if you know anything about the unit circle, you'll understand, because that's when you're at a quarter of the way, 3/4 of the way, a quarter of the way, 3/4 of the way, so on and so forth. Okay? So I know we went through those pretty quickly, but honestly, that's because this is like two full years of high school or a year of college. Next, we're going to look at piecewise functions and absolute value, and that's going to round out this review. The last topic we're going to review is piecewise functions and absolute value. Now, piecewise functions are simply when we have a single function that across its domain is defined by multiple other functions. Here I've defined it by 2 functions, but it can be defined by 3, 4, 5, 6, whatever. The important rule here is that each of the parts that are defining the original function have to be functions, and that the domain of the functions that are defining the piecewise function cannot overlap. I was trying to figure out the exact way to say that. Meaning that here I have x is greater than or equal to 4, and here I have x is less than 4. I could not say x is less than or equal to 4, because then I wouldn't know which function I'm using. I would have ambiguity here. And if you remember, our definition for a function is that each set in our range is assigned to exactly one set, or assigns exactly to one set in our domain. Basically, this points to only one thing here. If it points to 2 things here, not a function. Okay? So if this were a 5, for example, that would mean that our graph would extend to there, and you could clearly see that now this is not a function, because here at the point 5, we wouldn't know, are we here or are we here? Because our x value 5, do we use this f of x or do we use this f of x? So not a function at that point. So those are just a couple of things you have to be careful of when you're working with piecewise functions. Okay? Now, the reason we care about piecewise functions is because we care about absolute value when we start to work with the fundamental concepts in calculus. Because we're going to be working with distance, and absolute value is very much tied in with the concept of distance. However, absolute value is a little bit difficult to work with in this format. And if you remember, the whole purpose of absolute value is to always convert our value to positive. It's to take whatever our input is and give a positive output. So if you give 3 as an input, you'll get 3 as an output. If you give -3 as an input, you'll get -3 as an output. The issue is that working with that algebraically can become a little tricky. So the easiest way to do that is simply convert it into a piecewise function, because then it's very easy to work with, because you know, based on your domain, based on your input, which function you use, which version of the equation you're going to be messing with. So in this situation, you can test it. Just think about it. If you use 3. We'll use our 3 example. If I say 3, well, where is 3? 3 is greater than 0. Okay, so that tells me I'm going to use this. So I take 3, I plug 3 in. 3 would go in for x. 3 is 3, which means I get out 3. 3 is positive, totally works. Absolute value of 3 is 3. If I take negative 3, I would use this version instead. So negative 3, I put negative in, a negative negative, negative times a negative is a positive. So I take negative 3, put it in, the negative changes it positive, so I would get out positive 3, which is exactly what I'm supposed to get out of the absolute value. So this piecewise function version is exactly the same thing as what we're doing here with absolute value. So you're going to see that we're going to be using this a lot more often, so it's something to get used to. Now, if you have any questions about that or how that works or how it would look if you were to change up what this looks like, feel free to ask questions in the comments or jump into the Discord. We will be looking at transformations in the next video, so you'll see this a little bit more there and you'll see how that would affect the domain and how we would change that. So I hope you found that review of function families helpful. If you do have any questions, feel free to drop into the comments or jump into the Discord. In the next video, we're actually going to be looking at function transformations and operations. So that's going to be where you get to put pencil to paper, because after all, the best way to learn math is to actually do it, not just listen to somebody else.